Hello, this is the second lecture on our third design technique, which uses spring lever model and feasibility map. We had just mentioned the feasibility map in the last lecture. Today we will discuss how to construct it and how it is useful for designing, rather selecting and redesigning a compliant mechanism. So, let us look at this technique for constructing the feasibility map, and this is done with only user specifications and no other information, right, and then of course using the spring lever modeling. Okay. So, it is different from the other two techniques that we have discussed so far. So, the spring lever model, as you understood from the last lecture, it is merely an abstraction rather than a physical model, although in this particular example we are showing as if there is a physical model of the mechanism, like a lumped model where there is input side stiffness KCI and then output side stiffness KCO, and then there is lever ratio which is N. So, these are the three parameters which we said are the ones that one needs when you want to have an input output model for a 2 degree of freedom system. It is a terminal system, more like resistors and capacitors that we have electrical circuitry. Here we can actually think of this as a terminal model or port model. You have an input port or input terminal, output port, output terminal. What happens in between you capture using a few parameters. Here those parameters are this KCI, KCO and N. Again, the idea is it is only an abstraction and not a physical model. To emphasize that, we took this example in the last lecture, that when you have input and output, this particular spring lever, if I were to apply input like that, then you would expect this point to go that way, but here the output direction is this. So, there is a inverter mechanism, just to think of it as a physical model, but then these parameters, all of that is actually unnecessary. It is not a physical model, it is only an abstraction in the sense of a input output model. Here we have U in, this is the first one, and then we have U out, and there are forces F in and F out, and we have this matrix 2 by 2 matrix that connects the displacements and forces. It is like a lumped model, but 2 degrees of freedom, which separates out input and output in a way that output displacement is not n times input displacement. For a normal lever, if you take, you would have U out to be n times U in, but here it is not so. That is how it is constructed. This point here would have n times U in, whereas this point will not have n times U in, and that is what will be there in a compliant mechanism, that is what we are capturing. And likewise, if you choose this point where output is there, when you apply some force and displaces something, let us say there is a U out, input is not going to be U out divided by N, it is going to be something different, because it is a 2 degree of a model, you have to give actually 2 inputs to completely determine it, and that captures any compliant mechanism. So, we go by this, and now look at a problem, any problem that one may want to design a compliant mechanism for. We can say that there is a input port and there is an output port, and clearly in this one, if let us say input is in that direction, output is in that direction opposite, you cannot think of actually a lever. So, any lever that you think of here, it is not going to be anything physical, it is just abstract. So, we can just make a model such as this, where we have discussed all these equations. These are 2 equations here, these are equilibrium equations which we had derived in the last lecture by simply minimizing potential energy, and then we have these inequalities. These are important because these are the ones that are specified by the user. All of these are user specifications. These are easy for the user to specify, because user knows, let us say we take the previous example, if they have a piezoelectric patch, they would know how much force it can give and how much displacement or stroke that actuator can give. Most often piezoelectric patches, if I were to plot or if I were to plot force versus stroke, that how much the actuator. In fact, we can do that for any actuator. Any actuator will have force versus stroke curve which is characteristic for that actuator. Piezoelectric patches normally will have a characteristic that is linear because the displacement is very small. So, that will be within the linear regime of that material. So, this is a solid piezoelectric patch. When it deforms, it will be like a solid deformation, and its deformation is not much, you can assume it to be linear, it will be like this. What does this mean? When stroke is 0, when stroke is 0, you have the force the highest. At that point actuator has a lot of force to give to whatever it is connected to, but there will be a limit beyond which the force cannot be provided, beyond which it acts like a spring, right. So, now if you look force versus displacement, if you think of it, it has a negative slope here. So, a normal spring would be, if I were to do this for a normal spring, linear spring, if there is force and there is displacement, which is our stroke here, what we are calling stroke for an actuator, it will have something like this, is a positive slope, whereas here we have a negative slope. That is the meaning of an actuator actually. Looking at it, it is an actuator because its slope is negative, it is able to give the force in the direction of the displacement, whereas a spring will offer a force opposite the direction of the displacement. Okay. So, that is how it will be a linear actuator will be, and beyond certain point you need negative force, meaning it is not an actuator anymore, you have to supply the force by some other means. So, this is the limit, that is all actuator can move, that can push on some object for that stroke length, right. So, now what is happening? The force is decreasing as the stroke is increasing, which means that there is actually a spring in the actuator. If I take a piezoelectric patch, that patch or the material or a stack has to deform. In deforming, the material is being deformed, there is a spring. So, there is an actuator spring. That is why in the model that we show that connects to our SL model, we show Ka, that is actuator stiffness. So, when a user has an actuator in mind, the user would know what is the lower limit of the force and higher limit of the force, and likewise there will be an actuator stiffness, one can provide lower and upper limits. That is, if you have a bunch of actuators, then the user who wants to use the actuators and wants to design a compliant mechanism will know these values, how much force can be delivered by the actuator and how much stiffness will be there, and also the displacement at the input port Xn, how much displacement the actuator would have, right. And similarly, user would also know what they want at the output. So, they can specify the output force, how much they want if they want, and how much displacement they want if they want. So, those things are easy to specify. Additionally, we also have K external, where that comes from the object which is going to be there for the compliant mechanism to deal with. For example, in the previous case there could be an output load here, or there could be a spring, there could be a spring there which is K external. There could be both a spring and output load also, right. So, these are the things that are natural for the user to know, and that is what we take, these are the user specifications, right. From these and using the two equations, we have this spring lever model we want to construct. Rather, we do not want to construct the model, we want to see what values of KCO n and KCI will satisfy these inequalities and these equations, that is what we are asking. That is the crux of this SL model and also the feasibility map concept. we are not worried about the mechanism at this point. We just want to deal with user specifications and then inform the user, if this is what you want, this is what you want, we say this is what will be the parameter space of compliant mechanism. KCO, N and KCI is a triplet, no? You will have 3 values, there will be some value for KCI, some value for KCO and N. So, how many such sets will satisfy the inequalities and equalities, that is what we want to inform the user. If such a set does not exist, then the feasibility map will not exist. Okay? That is the idea here. Once you have this, then we can talk about K external and KA, which again are already there as part of the user specifications. In the context of those, we need to determine these 3 parameters. There could be several values if they exist, and that is what we want to inform the user. That is what we said last time also, and I am repeating now, that KCI N and KCI, KCO and N, if I have the 3 axes, right. Let us say this is KCI here and KCO and N, these are the 3 parameters. So, there will be a bunch of points, right. You can take a lot of them, only some of them will be satisfying our equations and the inequalities. We need to find that, and that is shown here. So, the volume that is shown here, this entire volume here, this volume is the one that contains all the feasible values of the triplet, feasible values of KCI, KCO and N. These are the ones that we want to calculate and show to the user. Now, there is no mechanism as yet, it will come, but right now we just want to tell the user how the specifications relate to these values. So, that is the crux of constructing the feasibility map. It is a map in 3 dimensions, but 3 dimensional map, even though you can draw with little difficulty, you can draw it, but on a computer screen, if you want to see, it is not as easy to manipulate and then see. That is, if you want to see, this is something, but in fact even here you do not know how the actual 3 dimensional shape is in one image of 2 dimension like it is taken now. You need to be able to really rotate this map and then see how the values of KCI, KCO N change. N can be positive or negative. In this particular case, N only has positive value because this is 0 and this is 10 and this is 5, this is the N axis in this case, but sometimes it could be negative also. What does that negative positive mean? It actually shown here, right. If N is shown in this manner, if I apply the force there, this because it is a lever, it will come down, N will be negative in this particular way. But if you want it to be positive, meaning that input force and input displacement, output displacement in the same direction, it can be positive also. So, N has that thing where it inverts the direction of the input force in order to produce output force, or rather the force at the point where the lever is connected, but sometimes it could be positive also. For that you do not have to worry about again a physical lever, just understand that N can be positive or negative. You will know what kind of a intrinsic amplification, that is what we call N is intrinsic amplification. It is merely kinematic or geometric amplification. We can see the range, that is entirely a consequence of the user specifications, or also in this particular case whatever the units they are, this needs to be 10,000 here, that could be let us say Newton meter, same thing here 4,000 for KCI, and we can see that range for the feasible map and then say, oh, this is how stiff the compliant mechanism should be for the specification that user has. So, when they enter some values, if you construct this map, you would immediately know what kind of a stiffness and intrinsic amplification that compliant mechanism that we have not yet designed or we do not know what it is, we know what it should be. This is similar to the way we choose materials for any design problem. We will have some specification in terms of stiffness, strength, stability, whatever, and based on those values we say, oh, this steel will be applicable, polymer will be applicable, or ceramic, we decide. In a similar way here, before we think about a compliant mechanism, we want to see the space. The space equivalent of material properties, we have properties of the compliant mechanism here, which are KCI, KCO and N, and that is the thinking that one should have with this third design technique. Once you have the 3-dimensional map that we saw, if I take a projection of that, we can do projection onto, in this particular case we are showing KCO and KCI. One can do KCI and N, KCO and N, any of the 3 combinations, that is up to the user and a particular problem. We will be doing case studies later where we will do KCI versus KCO, we will also do N versus KCI as well. So, we take those projections which are in 2 dimensions. When you do 2 dimensions, of course, we lose 1 dimension, because from 3D to 2D we are coming, in which case what will happen is the volume that we have, we take a slice. So, in the previous one, if I go and look at this one, let us say I want to choose a particular value of N, let us say that one, then I will be taking a slice there, whatever the shape that is, I will be taking a slice. So, that slice is what we are looking at in the next one for a particular value, but then we do something. You see this grayscale here, so somewhere it is completely white and somewhere completely dark, that indicates the N value. You can show that if you want, or when you have this in a computer graphics interface, user interface, as you mouse over on this, immediately N value can pop up. So, as you put here, 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 it will tell you what N value is. Low value and high value, not necessarily 0, some low value, high value, it can indicate that will be the grayscale. Okay. So, we can have that and see this, but idea is to be able to construct this map first. Okay. So, constructing this map, one may not actually need to understand or know in order to use this design technique. Design technique is you enter user specifications. As a user, you just enter what you want, that is all, you do not need to know anything more, but since it is a discussion of the technique, we need to understand the intricacies of how this map is constructed. Okay. So, here I am referring to the PhD thesis of Sudarshan Hegde at Indian Institute of Science. It is work, the title you can see, that is important to notice. It is a pragmatic design with regard to rigid body linkage based design or structure optimization based design. One has to learn a lot in order to design using those methods. Even if you have a software, you need to still know what equations you are solving. Here we are calling it pragmatic design because you are actually making it completely user oriented. User enters the values, upper and lower bounds. For that, user does not need to know about compliant mechanisms almost anything. He or she will simply enter the values. Then we show the feasibility map. If the feasibility map, let us say, is null, meaning that there is no set of KCI, KCO, N values that satisfies the equations, 2 equations we have, and 12 inequalities. There are 6 variables, each of them upper or lower. If there is nothing that satisfies, you simply tell the user that feasibility map is 0, null. Then user would know that what he or she is asking is not possible. Is not possible with any compliant mechanism, it is not possible at all with any mechanism, right, with that has this characteristic of the compliant mechanism, that is spring lever characteristic. It is not just 0 spring constant, it is all with springs, and there is a input output geometric amplification ratio. When is it not possible? So, when you have equations, you can have solutions sometimes which may be imaginary, but here some of the real solutions are also not valid because KCI and KCO cannot be negative. N can be negative, in which case it is just inverting the direction of the input when it gives to the output, but KCI and KCO cannot be negative. That is actually one criterion that we use to actually generate this feasibility map, and that is what Sudarshan Hegde did in his thesis. So, we will switch to the thesis. I will walk you through the chapter 4 of the thesis, where you can see how it is done. It is not straightforward, but at the same time it is not completely difficult, but there are certain things. So, I showed you the map which is like a continuous volume, singly connected volume. Is it singly connected volume, or there can be two separate disjoint sets? So, we are talking about KCI, KCO n values, they can be all continuous as one blob, or it could be multiple blobs also. So, what Sudarshan Hegde in his thesis has proved that it cannot be discontinuous, everything is continuous, it can be whatever shape. Clearly it is not a convex shape, it is non-convex, but it is singly connected, that is what he has proved. We cannot discuss all those details in the time that we have allocated for this particular topic, but I will give you the pointer as part of the supplementary material. You will be able to have access to the PDF file of this PhD thesis, and you will look at it. But what you need to understand first is the pragmatic aspect of this technique. So, we will switch to that and then come back to this. So, let us go to the PhD thesis. I am already on chapter 4, where he talks about the stiffness maps, because we are focusing on the stiffness, input side stiffness KCI, output side stiffness KCO for static applications. Later on we will be talking about dynamic applications also, right now it is only static. This chapter gives you complete details, I will just walk you through the important aspect. One important aspect here is that we have two equations. So, that we have inequalities are more difficult to solve, that is where the difficulty of this problem lies. So, equations we know, we have lot of different methods and many of them implemented in various software programs, but the moment you have inequalities the trouble arises, and that is what I will tell you how it is done here. We start with these equations, we have KCI some value is there, KCO some value is there. Now, on each of the variables that are contained in it, Fn, Ka, Un, F out, K external, U out, for all of these things we only have a range of values given by the user, and based on that we need to get range of values for KCI, but then n is also there. If you want to get a range, first thing to know is what is the minimum value, what is the maximum value, what is minimum value of KCI, what is the maximum value, but then n is inside, which is also an unknown here. KCO, we have F out and K external, U out and U in, n again is there. So, n is here and n is there, and that is what makes it difficult, because we do not know the range of n, we have to derive the ranges, feasible ranges of KCI, KCO and n. Even though we have two equations, if I know the range of n value, then I can get these two. For each value of n, I will know KCI, KCO, because I know these ranges, but then it is not just specific values of Fn, Un, everything has a range. So, everything here works with the range values. So, what we do here is pose a set of optimization problems where we try to make KCI or KCO only positive, we prevent them from becoming negative. That is, we try to find the values of n such that the resulting values of KCI, KCO for given range values for the 6 parameter that we have, they do not become negative, they need to be positive, that is the thing. So, by solving optimization problem in each case, by assuming different values of n, we need to find the corresponding minimum value of KCI as well as maximum value of KCI. Likewise, we get KCO, minimum value and maximum value. When you do that, what you get in between, there are some details that if you vary a parameter, that like here it is C, that will have a range that is generated. Within that you have to find the extreme values. A typical problem that we would pose here is like this. Let us say I want to find these blue boundary curves that are shown here. Let us say this is the feasibility map that is going to be computed, but we have not computed yet. So, what do? We take for a given, let us say KCO value, this is the KCO axis, this is the KCI axis. Let us say I prescribe a KCO value, let us say this line. Okay. Once I prescribe a KCO value, I still have n, that is we do not know, but I fixed KCO. Then I try to find whether values of n exist at all, and once I have values of n exist with our inequalities and equations, then I look at the KCI value. If the KCI value is positive, then I take it. If it is negative, I discard that KCO value, meaning that if I were to take a KCO, this is feasibility map, if I take a KCO that is over here, right, there is no corresponding KCI and n. That is what we decide by solving these inequalities and equations, by solving optimization problem, which I will show you. So, we can take slices of KCO and scan it from bottom to top or top to bottom, whichever way. Then for each case we try to determine the minimum value of KCI and then the maximum value of KCI. Then we generate this curve and that curve, right. In between we are just joining this, that may not be the case, for which we have to again do this reverse, that is we assume a value of KCI and generate extreme values of KCO. This is the KCO lowest for that KCI and the highest, and that is how we construct these maps. So, a series of optimization problems, they are not difficult optimization problems, they are simple enough, but they have to be done several times. So, a particular optimization problem that I will show you looks like this. So, for a chosen value of KCO, here we have put that as KCO S, meaning that specified a value that one level we have taken, then we have to minimize this KCI, for which we have an expression, but it is all in terms of the variables which have their own upper and lower bounds, and then we have subject to the constraint that the same values that I take should have the specific values of KCO. KCO is what we are taking, we want to find the extreme value, minimize we have to solve once, maximize we have to solve once. But then these are simple enough, because these are all polynomial equations, you can actually write down the Karush-Guntakar conditions for the KKT conditions and look at them analytically. We are not doing all numerically, we look at it analytically, and then we have the inequalities on U in and U out and other things, we put them all these other ones, and these n values also, there is an extreme value of n and highest and lowest, that you can determine by looking at the equation a little bit more. Again, all the details are difficult to discuss in a short lecture that is allocated for this topic. You can read this chapter 4, you can get that, but the gist is that we have to assume KCO and generate the side curves that I described in the figure above, and then do the reverse. You can assume KCI and get KCO, and Lagrangian, the usual way we write it, write this Karush-Guntakar or KKT conditions and solve this problem analytically. When you do that, when you solve it analytically, there is another problem that is posed, you can actually find a number of conditions under which there will be a particular solution. So, they are all conditions. When you analyze the KKT conditions, there are some intermediate variable that are defined like VH and so forth. So, when these conditions satisfied, you have a particular solution that is possible. Sometimes you go to, this is U in, U out, N, F out and K external. In this case, whether they will be at a high, it is somewhere intermediate, and then high, sometimes it is low and so forth. You check these conditions, they are all analytically obtained, you can get these various values and generate the boundary of the curve. Similarly, for another problem, we generate all these conditions, they are all simple enough. I am not saying that they are trivial, but they are not complicated in the sense that if we know optimization theory, we will understand this part, and with all of this we construct the boundaries here. We can construct a boundary for KCO given value and KCI, we can get this. Here we do not necessarily think that they need to be just joined, then you have to do KCI various things and then see what comes out here, if at all it is there. But we know that there is nothing below this, that is why this even dashed line is shown, because if I take KCO that is a value that is lower than this, it already tells you that we did not get a feasible n, we did not get KCI min this side, KCI max the other side. Another thing to remember, the moment we finish the map like this, okay, finish the map, any point I take inside can have several values of n. For KCI and KCO there is only one value, right, this is a slice, but there are several n values are there. So, you need to generate that whole n, that is the 3-dimensional volume that has a range. That n has to be continuous is what is also proved in this chapter. It is not like it goes like this and goes up, that actually continuous. Not only the feasibility volume is a singly connected domain, the n value at any point is also continuous, and that is also proved in this chapter for this continuity of n, right. So, this construction of this slice and that point is also discussed and proved. So, this chapter 4 is actually the key chapter of this thesis. Rest of it all is user centric, and user will be using it like more like a graphical user interface manner, but this construction of this is the key here, the continuity of n that I talked about between n low value and high value at any point it is a continuous value, and that is also proved by some analytical arguments. Okay. So, again I am skipping all those details, but telling you that what exists, these are all what you see here is the one that argues why it is continuous. So, anyway, now I would like to switch back to our thing here to say that with all of these, what we have discussed now is how to compute the feasibility map, how to compute the feasibility map. Chapter 4 in that PhD thesis tells you how to compute, but what you really need is that as a user, if you enter the specifications, we will get the feasibility map. Then what do we find from that? We first find if there is a solution or not. If there is a solution, that means that feasibility map is not null, you see some blob, okay, or projected one, you see some area. If that area is too small, then you would understand as a user that what you are asking is too stringent, that is such a small space of KCI, KCO n actually exists. It is saying, it is like saying that if you want to choose a material for a design that you have on hand, saying that my, let us say Young's modulus, we are talking about stiffness, Young's modulus has to be between 74 and 75 gigapascal, that is all, that small range. So, if you are lucky there will be an aluminum for you, but if you have some other value for which there is no material, or that material is not available in the form that you want, then you would know that what you are asking is not possible or very stringent, you have to go for a special material. Okay. So, it tells you the feasible space is very small, your specifications are stringent. Similarly, if the feasible space is very large, then you know that there could be many compliant mechanisms that will do your job, because what you are asking is commonplace. So, your KCI, KCO and N are all over the place, wide range, that one can expect that there will be mechanisms to meet your specifications. Okay. Now, let us say that you have done that, you understand that there is a solution and whether stringent or simple specification that you have. What we will discuss next is how to use this feasibility map to actually select a compliant mechanism. Okay. That is the next thing, and further reading for this apart from the PhD thesis are these two papers which we have also noted. This is the first paper there and this second paper that you can read more about what we will be discussing in this week's lectures. Thank you.